Okay, so this is the top view of the car. There's a wheel, and there's another wheel. And so the circle is the base of the car. You can think of the chassis. So really what I've drawn is basically a transparent base plate so you can actually see the inside of to see the wheels. Okay, so the two wheels are joined by an axle. And this is x0, that's y0. And a few dimensions. I'm going to assume that the distance between the two wheels of the car is 2b. So effectively, the distance, the distance between the two wheels is going to be b. So let me call that b. And then the tires are of radius r. Okay, and this is the position of the car at time t equals 0. Okay, so in this case, what I'm interested in is trying to keep track of this point on the car. In fact, you can keep track of any point on the car, and if you keep track of any point on the car, you can then find a position of some other point, because they are all at a fixed distance on the base frame, so it's very easy to find that. The reason why I chose this red dot is because it's very easy to keep track of that point as compared to some other points, but you can totally keep track of other points. So this is, I'm going to call this X. So let's call this point stuff, let's call it C. Okay, and XC0, YC0, and this is the position at time t equals 0. Okay, now, as I said, you can spin the wheels of the car at different speeds. So let's call this wheel as the right wheel. And so let's just say the speed of that one is v dot r. And then the speed of the left wheel. And so this is you can call either one right and left depending how you see, but let's just follow this convention, phi dot L. Okay, so this is basically that the car is going straight, and if you are actually seated in the car, then the left wheel is going to be the one I've shown, and right wheel is going to be the way I've shown it. Okay, so this is the position at time t equals 0. Eventually, when the car drives around, it ends up in a different position. So I'm going to essentially copy this and essentially redraw this. I don't think I can rotate it, but so that I'll have to redraw this thing. Okay. So when the car moves straight and then it basically is moving now and turns, you will have the axis at a different orientation. So now this axis is x1, y1. And the wheels are this way. Okay. Okay, so now this point, which is the center of the base frame, is going to be xc1, yc1. right? But I can also relate this to xc0, yc0, but that's at time t. So maybe I should make this distinction clear. This position here, which I drew, was actually xc0 at time t equals 0, yc0 at time equals 0. Okay, and this position which I drew over here, so let me rewrite this, is actually at a different time. So xc1 at time t, yc1 at time t. And then you can actually relate that to xc0 at time t, yc0 at time t using the rotation matrix, and I'll get to that in a bit. Okay, so this is the position of the car at some different time t, and let's say that the angle which the heading of the car makes with the horizontal is theta. So this is position of the car at time t. Okay, so what I'm trying to do now is I'm effectively trying to figure out the forward kinematics. So in case of manipulator, that was finding the angles of the, it was finding the position of the end effector given the angles. In this case, the forward kinematics problem is find the position of the car. So in this case, it will be xc at time t, yc at time t, and the angle theta given the driving history. So how you spin the two wheels, phi dot r, phi dot l, and also given the initial position of the car. So let me rewrite that. So forward kinematics. Okay, this is basically find xc0 at time t and yc0 at time t given, of course, the dimensions b, r. B is the distance between the two wheels, r is the radius of the wheels, given the driving history. That's going to be phi dot rt and phi dot lt, and the initial position. So that's going to be xc0 at time t equals 0 and yc0 at time equals 0. Okay. Now there's a difference between forward kinematics for a manipulator and forward kinematics for a car. For a forward kinematics for manipulator, we could find a position given the angles, and that was a formula, right? In case of a differential drive car, we cannot write a formula for xc0, yc0 the way we wrote it for forward kinematics. We only can write a formula for the rate of change of the position and velocity, so rate of change of position of the car, and then we'll have to do what is known as integration to find the position. So let me write that down. Unlike a manipulator where we got xq, yq as a function of theta 1 and theta 2, in case of a car, we will only be able to find xc dot t, y c dot t. We can integrate this differential equation to then solve for xc0 t and yc0 t. Okay, so that's the setup. Let's see how to find the rate of change of position. Okay, and the way we'll do this is we'll actually use the frame 1 to do it and then relate frame 1 to frame 0 using the rotation matrix we talked about earlier. So for that, I'll have to copy this figure. Can't seem to find the copy command. Is that this? No. That's the paste. Okay, I did not copy it. My bad. Huh. Never mind. Let me do it this way. Okay, I'm almost out of time. Let me just give a hint on what I'm going to do, and then I'll stop. So I'm going to try to write a formula for x c1 in and y dot c1, and then I will find, so that will be a formula, and then once I do that, I will then find x c0 and y c0, this using rotation matrix. If you want to give a thought over this, you can try it, else I'll do it. I'll anyway do it next time. Okay, so I'll stop here. I'm out of time, but I will see you on. Talked about modeling a differential drive car. Here is the figure I drew. Essentially, the circle represents the chassis of the car as you view it from top. The two wheels are shown. I would like to call the one on the, so if you think of the car moving to the right, like I've shown here, then the wheel to the right as you're going forward is denoted by r, and the speed of that wheel is v dot r, and the other one is the left wheel, and so that speed is v dot l. The parameters of the car are b, which is half the width of the car, so it's the distance, the width is the distance between the two wheels, and r, small r, is the radius of the wheels. Okay, so initially the car is in the position shown. X0, Y0 are the coordinate frames in the, that's the fixed frame which is going to be fixed, and we're going to keep track of the car with respect to that frame. So that frame is say the corner of a room where you're trying to locate the car from that particular corner. As time goes by and you make the car move by spinning the wheels, the right and left wheel, at some different time t, the car will be in the position shown in the figure below. It will have made an angle of theta with the original x-axis, and the position of a point C, which is a point midway between the two wheels, would be denoted by xc1 and yc1. The one denotes a new frame, 0, 1, x1, y1. So our goal here is to figure out the forward kinematics of the car. In general, if you can find the position of any point on the car, in this case I chose point C. If you can find the position in frame 1, then we can find the position in frame 0, which is the base frame. And if you know the position as a function of time t, then you can actually go back and relate it to, basically can plot the whole car if you know, because it's a rigid body and every point on the car is at a fixed distance from the point C. So I'm going to do derive an equation for the forward kinematics, which is the problem, find the position of point C as a function of time. Now, a big difference between a car and a manipulator is that for a manipulator, you had an explicit formula for the end effector or the tip of the hand for the two-link manipulator. In this case, we will not be able to find a explicit relation for the position C. We'll actually write a differential equation for C, which is x dot C and y dot C, and then integrate that as a function of time to get the position uh, from the velocity. Okay, so now what I'm going to now what is going to follow is a derivation for the velocity first in frame 1 and then frame 0. Okay, so let's do that. Here's this. Okay, so here's the formula for velocity of x of point C. Okay, so drew the car and then I showed the frame 1, so x1, y1. Here I'm only showing the point C, and let's for a second assume that phi dot r is 0. Okay, so the left, sorry, phi dot l equals 0, which means that the left wheel is stationary. Let's assume that phi dot r is not equal to 0, which means that this point is not 0, and so it's going to move a slight distance front. Okay, so we know that the distance between, well, before I do that, when a, okay, so let me draw the wheel. Okay, this is the wheel, and as I said, the radius is r. Okay, and since the wheel has a speed of phi dot r, which is not equal to 0, the distance moved by the center of the wheel, okay, this distance is r times phi r dot, right? Why is that so? It's because the arc length is r times phi r, okay, or the circumference of the circle when for a phi turn in the phi rotation of the circle, the arc length covered would be r times phi r, and that's going to be the distance moved in front. If you then take the rate of change of that arc length, you get essentially the speed. So this, let's call that, okay, maybe a better way to show that is, let me redraw this. Okay, this is, let's say, the initial point. This is phi r. Then we know that this distance is actually, let's call that arc length, is phi times r times the radius. So then the distance moved in the forward direction when the wheel turns by phi r is going to be, this is basically x, is going to be phi r times r. And so when you take the derivative of this, you get r times phi r dot. Okay, but this happens to be the motion of the center. So what I can do, coming back to the original figure, is that so this is not to be confused with the wheel. So this is the wheel. This is also the wheel. And this is the car. Okay, so don't confuse the circles. They're not the same thing. This is basically showing this part of the car. Okay, the same thing here. So what I was trying to make the argument that when phi dot r is not 0, then the distance moved by this point is going to be one sec. This is better. This distance is going to be r times vr dot. Okay. Okay, let me redraw this because now I'll be deriving the velocity. So circle point C, this point is at rest, so velocity is 0. This point has moved by distance r times vr, so its velocity is x. Let's call this wheel right. So x wheel right is going to be r times vr dot, and this is in frame 1. So then the question is, what's the distance or what's the velocity of point C? You can see that just from this drawing that the distance moved by C is actually going to be half the distance or half the velocity of this point. So from this, we can write xc1 dot equals 0.5 r phi r dot from geometry. Okay, and that's only because this point C is exactly midway between the two wheels. Okay, so if the left wheel is at rest, the right wheel is not at rest, then the velocity is this. We can use the same arguments for the opposite way, which is phi dot r equals 0, phi dot l is not equal to 0, and then we'll see that we can actually derive that the velocity of point C in frame 1 is 0.5 r times phi l dot. Okay, there's a question. What phi dot phi? So the question is, would phi times r dot be the arc length? No, the arc length is phi times r, and the rate of change of arc length is phi times r dot. So this is in response to the question. Arc length is r times phi. Okay, so remember that arc length is nothing but this thing here, but it also happens to be the distance moved by the center, because if there's no slipping, then this distance, let's call that x, is also equal to the arc length, and then x dot, which is the distance moved by the center as a function of time, is going to be x dot equals r phi dot. That just follows from taking the derivative. Okay, so we've derived an expression for x dot c. Okay, another question. Isn't phi L 0? Phi L, yeah, so this is for the first case when phi dot L is 0, phi dot R is not equal to 0. So that's the distance moved, the velocity of point C is given by this formula. If the opposite is true, which is phi dot R equals 0 and phi dot L is not equal to 0, then you would have something like this. Right? This is going to be x dot WL equals R times phi dot L. And then this distance is basically given by x dot C1. So it's basically doing the same arguments 2 times. So these are 2 special cases when one of the speeds is 0. If both the wheels are spinning, then actually x dot C in frame 1 is going to be the sum of the 2 speeds. So phi dot R plus phi dot L. Okay. So that's the expression for the speed of point C in the x direction in frame 1. Okay, frame 1 is this one, and the y direction is exactly right angles to x1. Okay, so that's the speed of x, the speed in the y direction. Okay, can somebody guess what that would be? The speed in the y directions. What's y dot c1? you can just say it or you can type it. What's the speed of point C in the y direction when either the left or the right wheels are spinning? Nobody? Okay, it's zero. Yeah, that's right. So it's going to be zero. And that's simply because this frame is, as I said, fixed to the robot. And when the wheels move straight, they are not allowed to move at right angles to uh, the direction of motion, which is along x1. So it has to be zero. Okay, so that's right. So this is these are the speeds in the frame 1. Now we need to find the speed in frame 0 because ultimately we want to relate everything to the fixed frame. Okay, so what we now do is we use the formula for rotations. So c dot c0 dot equals r10 c dot, where c dot 0 is going to be x, c dot 0, y dot 0. Rotation is cosine theta minus sine theta, sine theta cosine theta, and then the speed is something which we just derived, y dot c1. Okay, so subbing in the values, we have 0.5 radius times phi dot r plus phi dot l, and then 0. Okay, so we can expand that out to get two formulas, one for x dot c. Okay, and I'll just make this clear. It's basically we are finding the velocity at a certain time t. It's not at time t equals 0. We still need to find uh, the position from this velocity. So multiplying the terms together, we get, actually it's actually quite simple, 0.5 r times phi dot r plus phi dot l times cosine theta, and y dot c0 is 0.5 r phi dot r plus phi dot l sine theta. Okay, okay, note that speed in the y direction in frame 0 is not equal to 0, although the speed in frame 1, this one, was 0. But the beauty of this is, of using these frames, is that speeds in one frame are really simple in frame 1, and then speeds in frame 0 are not that simple, but they're easy to derive because we've already developed a formula to relate speeds from one frame to another frame. So that's one of the big advantages of using frames of rotation, which we've seen in a few lectures before, and we're also useful for the manipulator. Okay, so we are not done yet. We found how the point C changes, but there's another variable in the figure which I have not yet derived a formula for. You can see that a car is given by two things. One is the speed of point C, so that telling you how the car is moving forward. But then we also need to keep track of how the car is rotating. So theta determines the steering of the car, right? And that's also a key thing we need to keep track of. So what we'll do next is we'll try to derive a formula for phi dot. Okay, again, you cannot derive a formula of phi, but you can derive a formula for phi dot. So next part is derive expression for steering, which is theta dot. Okay, now the arguments are going to be very similar to x dot. Let's see how that goes. Okay, so first of all, Let's draw the chassis. We have point C, the two wheels, okay, and we'll have the same argument, which is we'll assume that uh, left wheel is stationary, the right wheel is turning. Okay, so when the right wheel is turning and the left wheel is stationary, this is not going to move. The left point, the right point is going to move. It's actually going to go like this, right? And we also know that this distance, which is the distance between the two wheels, is b, or 2b, sorry. This is 2b. Okay, we also know that the radius of the wheel is r. Okay, so now I think I'm all set to derive the formula. So as I said, if you draw the wheel, okay, this is the chassis, then the distance moved by the center is going to be x equals r theta or r phi, and then the x dot equals r phi dot. Okay, so that's going to be r phi dot. Okay, that's the speed. But in that time frame that the right wheel moves forward by distance r phi or velocity r phi dot, we would see that this chassis actually turns by an angle theta, right? And that theta, so given this theta, given this 2b, we can actually write a formula for this arc length. This arc length is going to be 2b times theta. That's the arc length. But in this case, we are trying to find the rate of change of arc length. So the speed is going to be simply 2b times theta dot. So I'm just taking the derivative of both sides to get the expression for the speed. So we have two formulas. One is, so let's call that x dot wheel. There's also x dot wheel. So x dot wheel can be written two ways. One is we write it as r times phi dot. That's by looking at the wheel. We can also write it as 2b times theta dot. This is by looking at the chassis, the top figure. And then if you equate the two, we get theta dot equals 2b divided, sorry, it's r divided by 2b times phi dot r. Let me not underline that because there's more arguments. Okay, so this is basically how much the wheel would turn counterclockwise, right? You can imagine if the left wheel is at rest, this is the left wheel, and the right wheel is turning, then the chassis is going to turn counterclockwise, and so that's going to be the expression for the heading change, right? We can do the same argument, we can use the same argument for the wheel turning the other way, which is now saying that the right wheel is at rest and the left wheel is turning. Then you'll have the chassis sort of pivoting about the right wheel, and then you will have an angle of now minus theta because the chassis is going to turn clockwise. So you can write this two ways. You can write it as 2b times theta dot, which can also be written using arc length r times phi dot l. But remember, this is negative because it's turning clockwise. So we can write minus 2b theta dot equals r times phi dot L, and so theta dot equals negative r phi dot L divided by 2b. So what we can do now is combine the two expressions. One is for the left wheel, one for the right wheel, and the net rotation, if both wheels are moving and not stationary, then is going to be phi dot equals r divided by 2b phi dot r minus phi dot L. And so that's the expression for the rate of change of uh, theta, or the heading. Okay, so in summary, I'm going to put all the formulas down in one place. X dot C0 is 0.5 r phi dot r plus phi dot L cosine theta. Y dot C0 equals 0.5 r phi dot r plus phi dot L sine theta, and theta dot, should use small letters here, is r divided by 2b phi dot r minus phi dot, write this as 0.5. Okay, now one simplification, if you read other textbooks, is that they don't really write phi dot r phi dot L, because that's writing too many things. What people do is they normally simplify this expression in the following way. They write v equals 0.5 r times phi dot r plus phi dot L, and omega equals 0.5 r divided by b phi dot r minus phi dot L. And the reason you do this is because now if you plug in these values, then the expression becomes pretty simple. Also, once you find v and omega, it's not too hard to find the corresponding phi dot r and phi dot L. So remember that phi dot r and phi dot L, which is the speeds of the left and right wheel, is the input to the robot. That can be, once you give that, it's easy to find v and omega. And then v and omega are then related to the formula for position of point C, which is now given by, this is simplified to the following. Frame 0 is v cosine theta, y dot C0 is v sine theta, theta dot is omega. So these are the equations which you will see if you read a text, or if you're reading papers. That's the expression you'll see. Okay, so for all practical purposes, we will use this formula. For simulation. Okay, so as I said, we eventually interested in finding the position of point C, but we've only been able to derive an expression for the velocity of point C. So how do you find the position? So to find position, xc0, yc0, and of course we also need to know the heading, because we know which direction the car is going. We need to integrate those equations. Okay. One of the simplest way of integrating equations is what is known as Euler's method. If you have forgotten what that is, it's basically taking finite difference. So x dot c0 can be written as xc at time I plus 1 minus xc at time I divided by delta t, so ti plus 1 minus ti equals v. In this case, since velocity is going to change at every instant of time, I need to write velocity as velocity at ti cosine of theta, which is again going to be at time ti. So write this down. I do the same thing for y dot c. V of ti sine of, okay, and then for theta, theta at time I plus 1 minus theta at time I divided by ti plus 1 minus ti equals omega at ti. Okay, so let's rewrite that as x c at ti plus 1 equals xc at ti plus, I'm going to call this expression as h. Okay, that's basically the time width. I'll just simplify my expressions. V of ti cosine of theta ti yc ti plus 1 equals yc ti plus h times v of ti sine of theta ti. And then finally the heading, which is theta ti plus 1 equals theta ti plus h times omega ti. Okay, so here we need to numerically integrate, which is given xc at t equals 0, yc at t equals, sorry, I just need to put frame 0 everywhere. This is fine, doesn't need frame. That's it, yeah. So y at t0 and theta at t equals 0. Okay, so this is given. Once we know the position and heading at time t equals 0, we can then progress this over time by just using this three formulas to find the position of point C at a different time t. And then once we get the position of the point C, it's fairly easy to draw the animation of the car because every point on the car is at a fixed distance from point C. So what I'm going to do next is show you an animation of how, but simulation and then animation of how to simulate a car in MATLAB. And so that this is basically doing the forward kinematics problem. Okay, so let me run the program first. Okay, so you just barely saw it. It's basically a car which was drawn as a circle, and it just basically drew the letter L. So what goes into the program is basically the inputs to how you want to control the car. So as I said, v equals 0.5 r phi dot r plus phi dot l is the velocity, and omega is given by this expression, and we need to set this. So one of them, v, basically sets the forward progression speed, while omega sets the direction in which you're going to move, right? And so what I did here was essentially set the speed to be ones, so it's going at unit speed, and the direction was set to 0. That's for a time from 0 to 1, so 1 second. Then from 1 to 2 seconds, I basically got the car to not speed up. So it's going at 0 speed. So it's not moving effectively, but I set the direction to be pi by 2, which means it's turning by a constant. So you saw that it actually went down and then it actually turned to proceed to get the horizontal line in the L. So then from 2 to 3, it basically had speed of 1 and 0 for the direction. So running this again, it had 3 motions, turn and then go. So again, I'll play it. Let me increase the delay so you'll see it. Make this 0.2. Okay, so the 3 maneuvers: go straight, then turn at 0 speed, and then go straight. Okay, so what goes into the program is, so that's how I command the car, but this is the code which simulates, which does that integration which I talked about, those three equations. So I call that Euler integration because that's called the Euler method. The Euler integration basically takes in the formulas for x dot, y dot, and theta dot, and then uses the Euler's formula, which I just wrote down. It's x1 equals x0 plus x dot c, which is the speed times h. Okay, and then it just does it for whatever time span I want this to. Okay, so question, is the xc after given supposed to be in frame 02? So everything I've derived here is in frame 0. Nothing is in frame 1. If I do everything in frame 1, then I cannot animate it. I need to get everything in frame 0. Frame 1 is only used to make my life easy in terms of deriving the expression. So this is all in frame 0. Okay. If I'm sorry if this was confusing, it was just indicating the time. If you want, if it's easier, you can call that T1, T, T. So that's the time index. So hopefully this will make it more, slightly more clear. To call this T and this T. Let's see if it runs or gives me an error. Oh, there's an error. So the other thing is when you work with MATLAB, and this is kind of important, is you don't need to second guess. It basically tells you explicitly where the error is. So when I ran this program, it says unrecognized functional variable theta 0, and that's on line 12 in Euler integration. So if you want, you can go to Euler integration by clicking there, or you can just click this line 12. It actually goes directly to the place where it saws error. So you can see that there's theta 0, and that's undefined. And that's because I just redefined it here. So let me change that to T0. Okay, and see if that works. Okay, now it's saying line 19. So I click on there, line 19, there is missing T. Okay, try again. Okay, so it worked now. Because there's one more thing I need to tell you about this code, which is when you do this simulation in using Euler's method, I need to use a very fine step size to get this uh, not have numerical issues. I use 0.1. If you actually use 0.1 for animation, then the animation will go very slow. That's because there are too many data points. And so what I do here is I actually downsize the data by using this function called inter. It basically interpolates the data. So if you have 1,000 data points, you can get them down to 100 data points by using this interpolation. And I would recommend that you try to search this yourself and see how interpol works, and then understand how I using this in this code. Essentially, I'm just interpolating x, y values so that they are downsized by a whole lot. Okay, and then the animation routine is pretty much what we did with the patch. Okay, there's a patch and there's a line because I want to draw the L. And you should be able to follow this given that we've talked a lot about animations previously. Okay.